morning, students. Today we will be discussing about the remaining topics in the moving charges and magnetism. So, in the previous classes we have studied about the circular current carrying coil and the Ampere circuital law, and based on the Ampere circuital law we have studied the first application, that is calculation of magnetic field due to an infinite long solenoid. And the second application based on this Ampere circuital law is solenoid and toroid. The second application that we are going to discuss based on Ampere circuital law is solenoid. Then what is this solenoid? Solenoid is a device which is used to produce uniform magnetic field. Uniform magnetic field in the sense, it is a field where the magnetic field intensity is same throughout the space what we are considering. That means both in magnitude as well as in direction, its strength remains the same. So, solenoid is a device which is used to produce the uniform magnetic field. Just like the capacitor is a device which is used to produce the uniform electric field. So, in the previous chapter, that is in electrostatics, we have studied that a device which is used to produce uniform electric field is, an example for it is capacitor. In between the plates of capacitor, the field is uniform. In the similar way, what is a device that is used to produce uniform magnetic field? Means a best example for it is solenoid. So, what is solenoid and how it is going to be prepared? Solenoid is nothing but it is looking like a spring like structure or helical structure. We will take a copper wire which is coated with the insulated material. When this copper wire is winded on a hollow cylindrical material, then we are going to get a solenoid. So, that means if this is a hollow cylindrical material, this is a hollow cylindrical material, over this hollow cylindrical material we are winding an insulated copper wire with the windings closer to each other like this. This arrangement is said to be the solenoid. So, what is a solenoid means? It is nothing but a insulated copper wire which is winded over an hollow cylindrical material. So, this is a solenoid, and inside this solenoid we are going to get the uniform magnetic field. So, how we are getting this uniform magnetic field we will discuss here, and based on the Ampere circuital law we are going to discuss about this solenoid. Calculation of magnetic field inside the solenoid we are going to calculate. Now, if you see here, the wire is coming like this and it is going in this way. So, that means if it is the hollow cylindrical part, a wire is taken like this and it is winded in this way. So, or else you can wind like this, you can wind like this. Now, from this side I will take the cross sectional view here. If I taken the cross sectional view, let me take this cross sectional part of this solenoid, and here the wire is coming out and here it is going inside. So, here it is coming out. I have told you previously that a physical quantity which is coming out is represented with the dot, and the one which is going into is represented with the into mark, encircled into. So, here the dot is going to represent, it is coming out, the wire is coming out, and here it is going into, therefore into mark. So, encircled dots indicates the wire is coming out, and encircled intos will indicate the wire is going into. So, like this we are going to represent the solenoid schematically. So, wire means through the wire what is passing, through the conducting wire current is going to be passed. Therefore, here current is coming out and here current is entering into the board. So, I is nothing but the physical quantity which is coming out here and it is going into the board here. So, I current is coming out and I current is going into the board. So, now in this one we are going to calculate what means, we are going to calculate the magnetic field along what? Along the axial line of the solenoid. Now, regarding the solenoid, we are going to discuss here about the infinite long solenoid. What is meant by infinite long solenoid? Infinite long solenoid in the sense, its length is very much large compared with its radius of cross section or area of cross section. That means, if you take a, for example, simple example for it is, in the first year part in capillary tubes, we have studied about the capillary tubes. Capillary tube means what? Its length is very large compared with its area of cross section. For example, if you take the refill inside the pen, the length of the refill will be large compared with its radius of cross section or area of cross section. If this is the area of cross section and this is the length is very large compared with the areas of cross section, then I can take it to be a capillary tube in first year what we discussed. In the similar way, infinite long solenoid means the length of the solenoid must be very large compared with its radius of cross section r. L should be far greater than r. This is a condition for infinite long solenoid. As an example, if there is a solenoid of 1 meter length, and radius of cross section is equal to 0.5 centimeter, I can treat it to be infinite long solenoid. So here infinite in the sense practical infinity, not the theoretical infinity. Theoretical infinity is different from the practical infinity cases. So practical infinity cases only we are discussing here, but not the theoretical infinities. So whenever the length of the solenoid is very large compared with its radius of cross section, I can treat it to be an infinite long solenoid. So 1 meter is far greater compared with the 0.5 centimeter. This is in centimeter, this is in meter, and this is very large compared with this one. Therefore, I can treat it to be infinite long solenoid. Understood? What is the definition for infinite long solenoid? A solenoid whose length is very large compared with its radius of cross section is said to be the infinite long solenoid. Now here I am choosing a solenoid of length L and radius of cross section R, and we are going to calculate the magnetic field inside this solenoid. Inside this solenoid, let us consider point P. So what is the magnetic field intensity due to this solenoid at this point? For understanding this, we are going to use the Ampere's circuital law, and this is we are going to calculate the magnetic field inside the solenoid using the Ampere's circuital law. For that, let me choose the solenoid like this. Let me draw the solenoid in this way. The schematic representation more clearly we are representing here. So let me choose it is a part of the solenoid. So what is a solenoid? A solenoid is nothing but an insulated copper wire which is winded on an hollow cylindrical material in the form of a spiral arrangement. Now here the current is coming out here, therefore it is encircled into, it is coming out, current is coming out, or the wire is coming out from this part and it is entering into the board from this side. So into indicates the current is entering into the board and dot indicates the current is coming out of the board. So this is how we are schematically representing the solenoid. So I am going to calculate the magnetic field well inside the solenoid using which one? Ampere's circuital law. So let me choose, this is the axial line. This is the axial line of the solenoid. Let L be the length of the solenoid. L be the length of this infinite long solenoid. Infinite length solenoid in the sense its length is very large compared with its radius of cross section. Now inside this we are going to choose an Amperian loop. This is an Amperian loop. Here the Amperian loop is of a rectangular shape. Let the loop is named as ABCD. What is ABCD? ABCD is a Amperian loop which is of rectangular shape. Let L here, this length you take it as some h. So AB is equal to h. AB is equal to h and CD is also equal to h. Let me choose this length is equal to some B. This is B. This is B I am choosing. Now let us consider in this one capital N number of turns are there. The solenoid is consisting of how many number of turns? Capital N number of turns are there. So let N represents the number of turns. Let capital N represents the number of turns. Let capital N represents total turns in the Amperian loop, in the Amperian loop. Amperian loop. So how many number of turns are there in this Amperian loop? I don't know. I have to calculate the number of turns in this Amperian loop. Let I be the current here, which is coming out here and which is entering here. It is coming out of the board and here current is going into the board. Now here, for example, if we count here 1, 2, 3, 4, 5, 6, 7, 8. 8 number of loops are there as an example here. But I don't know, this length is h I have taken, I have to find out how many number of loops are there or how many number of turns are there. For that, let n be the, n represents the total number of turns in the Amperian loop. In order to find out this, choose small n as the number of turns, per unit length, of solenoid, per unit length of solenoid. So arbitrarily what we are choosing means small n is going to represent the number of turns per unit length. That means small n is equal to total number of turns, divided by total length. So now, if small n is the number of turns per unit length, how many number of turns are there in h length? Per unit length, small n number of turns are there. Then per h length, how many number of turns are there? Suppose if I know the cost of one chocolate, I am going to calculate the cost of any number of chocolates. If the cost of each chocolate is 2 rupees, what is the cost of 3 chocolates? 3 into 2, 6 rupees. If the cost of one chocolate is 2 rupees, what is the cost of x number of chocolates? 2 into x. In the similar way, if I know the number of turns per unit length, then the number of turns per h length will be, number of turns per unit length is n, which is representing the cost of each chocolate. Then how much length is there? H length is there. Then what is the total number of turns in this Amperian loop? Means the number of turns in this Amperian loop is nothing but number of turns per unit length into the length of this. That is, therefore, capital N is equal to what I can say? Small n into h represents what? Represents number of turns in Amperian loop. In Amperian loop. Is it clear? Now, if one turn is there, I current is coming out. 2 turns, 2I current. 3 turns, 3I currents. 4 turns, 4I current is there. Then what is the total current inside this Amperian loop? Total current inside the Amperian loop is how much? Total current inside Amperian loop, is nothing but I inside is equal to total current inside the Amperian loop is equal to number of turns into the current through each turn. That is I is the current through each turn. Now I got the current enclosed inside the Amperian loop. But what is the formula for Ampere circuital law? From Ampere circuital law we know that, Ampere's circuital law, we know that closed line integral of B bar dot dl bar is equal to mu naught into I inside. This is the basic formula what we discussed using the Ampere circuital law. So this is the basic one. So here, if you see magnetic field, how it is going to be changed here. If you see this one, inside the solenoid, the magnetic field will be uniform. The magnetic field inside this solenoid will be uniform. Solenoid is a device which is used to produce dash kind of magnetic field. It is a device which is used to produce uniform magnetic field. Just like a capacitor is used to produce a uniform electric field, this is used to produce a uniform magnetic field. So, this is B term, this is H. See here. So, solenoid is a device which is used to produce which kind of magnetic field? It is a device which is used to produce a uniform magnetic field. Now, the field B is uniform here and it is directed like this. Over the length AB, the magnetic field is parallel. Therefore, from here to here, A to B, length and magnetic field, that is AB length and magnetic field, they are parallel to each other. So, theta is equal to 0 in this case. From B to C, B bar and this length is perpendicular to each other, theta is equal to 90. So, theta 90 means according to this B bar dot DL bar, A bar dot B bar is there means A bar dot B bar means AB into cos theta, where theta is the angle between them. Yes or no? According to that, over this length, theta is equal to 0, theta is equal to 90, cos 90 is 0. That means over BC it is 0, over AD also it is 0, over AB, AB is parallel to this B bar, therefore theta is equal to 0, cos 0 is equal to 1. Over CD, what is its value? Over CD, here the magnetic field is almost 0. It is taken almost 0, not exactly 0. When you compare the magnetic field well inside the solenoid, the magnetic field outside the solenoid is negligible. It is not 0, but it is negligible. I will tell you why it is negligible and how the magnetic field inside the solenoid will be uniform. I will discuss later. So, first I am considering here the magnetic field outside the solenoid is 0. So, now according to that rule, using this formula, what I am going to say? See this one, closed integral, line integral extended from A to B, B bar dot DL bar plus closed integral extended from B to C, Amperian loop I am choosing, B bar dot DL bar plus closed integral, line integral, closed line integral extended from C to D, B bar dot DL bar plus closed line integral extended from D to A, B bar dot DL bar is equal to mu naught into I inside. Yes or no? So, we have to integrate the magnetic field over the entire loop, Amperian loop A, B, C, D, A. Therefore, A to B, B to C, C to D and D to D, which will complete the Amperian loop. From this, closed line integral of over A to B, what is the angle between B bar and AB? It is 0. Therefore, I can write as B into this length, this is DL into cos 0 plus this value will be B bar B into DL into, or this, what is this? I can repeat A to B here and B to C here. This angle will be, B bar is like this length is like this. So, angle between them is 90. So, cos 90 plus integral C to D. Here B is almost taken as 0 because B is negligible outside the solenoid. Therefore, 0 into DL plus closed line integral from D to A, B into DL into, here B is like this and this, here theta is equal to 90 degrees over dA. Therefore, it is cos 90 degrees is equal to mu naught into I inside. Is it clear? Now, if you take this into consideration, I will be writing it here. Now, see here, cos 0 is 1, B into DL is there, B is uniform, that means it is constant, constant can be taken out of integration, therefore, I can write it as B being uniform, it is constant, therefore, I am writing it out of integration. This is A to B of DL plus this value cos 90 will be 0, therefore this entire term will be 0, and here B is 0, 0 into something will be 0 plus 0 plus this is cos 90 will be 0, therefore this term will be 0. That is equal to mu naught into I inside the Amperian loop. Is it clear? So from this, B into what is the length of AB? Length of AB is nothing but h I have chosen. Therefore, I can take it as h plus this is 0, 0, 0. Therefore, I can directly take it to be this part is 0. Therefore, B into h is equal to mu naught into I inside. Already we calculated the value of I inside. I inside value is how much? This you take it as 1 and this you take it as 2. I inside is n into I. This implies n into I using equation number 1. Using equation 1. From this, B into h is equal to mu naught into what is this n here? N into I we are having, n is nothing but small n into h. Therefore, I can write it as small n into h into I. From this, h and h is going to be cancelled, and what is remain? B is equal to mu naught into small n into I. This is the formula for magnetic field well inside the solenoid. So, what is the formula for magnetic field well inside the solenoid? B is equal to mu naught Ni. Is it clear? This is a useful formula for all kinds of competitive examinations. B is equal to mu naught Ni is the formula for magnetic field well inside the solenoid. So, here I told you that magnetic field inside the solenoid is uniform and outside the solenoid it is negligible. When you compare that magnetic field with the magnetic field inside the solenoid, I will tell you how it is neglected in the next part. Is it clear? So, first what we have discussed here, we are calculating the magnetic field inside the solenoid using Ampere's circuital law. So, it is one of the applications of Ampere's circuital law. First application what we studied is calculation of magnetic field due to an infinite long straight wire using Ampere's circuital law. Second one is calculation of magnetic field for the solenoid case. So, here why it is to be insulated copper wire. If it is not insulated, when the windings are close to each other, the copper wire is conducting, therefore, the current won't pass through the turns, but it will be these two coming in contact with each other, the current won't pass in this way. That is why it must be insulated. Insulated copper wires will be taking. That means insulated copper wire means a copper wire is taken, over that a wax coating will be given which will serve as insulating material. Though two turns comes closer to each other also, there won't be any conduction between the side by side turns. Is it clear? That is the importance of insulated copper wire. So, here what is a solenoid means? It is a device which is used to produce the uniform magnetic field, just like the capacitor is going to produce the uniform electric field. This is very important, that is to be remembered. Is it clear? Now, this is about the solenoid. What is the final answer we got? Magnetic field inside the solenoid is given by the formula B is equal to mu naught Ni. Here N is not the number of turns, but it is the number of turns per unit length of the solenoid. Be cautious, small n is the number of turns per unit length, not the number of turns. I is the current through the solenoid and B is the magnetic field. So, here magnetic field is related linearly with the current inside the solenoid. And it also depends upon mu naught. That means it is depending upon the material, core material inside the solenoid. If air is the core material, we are taking it as mu naught. Sometimes in the next coming classes, we are going to study that the core material may be some soft iron will be taken. In order to increase the magnetic field inside the solenoid, we can replace the air core with some magnetic materials like soft iron. So, whenever some other magnetic material is kept inside the solenoid, this B is going to be affected. So, B depends upon the core inside the solenoid, it depends upon the number of turns per unit length of the solenoid linearly, and it also depends upon the current linearly. This is about the solenoid. And next I will discuss why this magnetic field is uniform inside the solenoid and why it is going to be taken as almost 0 outside the solenoid. Is it clear? Okay. Look here, ma. We have discussed that magnetic field well inside the solenoid is uniform. Why it is uniform is the question, and outside the solenoid I told I told that magnetic field is almost negligible compared with the inside magnetic field. What is the reason for that? A solenoid is nothing but in a spiral arrangement like this, which is made up of copper turns only, and here I is the current passing. And here each turn of this solenoid can be treated as a current loop. If each turn is treated as a current loop, in the previous concepts we have studied the magnetic field due to current loop will be directed along the axial line. So, we have used the rule according to the thumb rule or clasp rule. If this is the coil, I am keeping it like this, and if current is coming in this way, then magnetic field is directed along the axis I told you. And even we can use the thumb rule like this. Suppose this is the direction of current, this represents the magnetic field. Suppose if it is straight, if it is a straight conductor, if current is passing in this direction, then magnetic field lines will be along the length of conductor in circular pattern like this. So, in the similar way, if you treat it as small elements, circle can be treated as a straight wires. Therefore, if it is taken like this, here the magnetic field is like this, here it is like this, here it is like this, here it is like this. So, what is the magnetic field means? Here the magnetic field will be in this way. If current is passing in this way, if current is passing like this, then this will represent the magnetic field lines. Current is passing in this way, I is passing in this way, and around this magnetic field lines will be. So, current is passing in this way, so magnetic field lines will be in this way. This is the representation of magnetic field lines. Is it clear or not? This is magnetic field. Or only one part I will be considering. Here current is coming out like this. If I take this part, it is coming out in this way. So, here only one part I am choosing. So, here this is the direction of magnetic field. Is it clear? Understood this clearly? Like this, at every part of the loop, the magnetic field is encircling. So, here also the magnetic field will be encircling like this. Here the magnetic field is coming like this and going out like this, in this way. So, if I take the magnetic field direction, here if you see, magnetic field is in this way outside the solenoid, and inside it is in this way. So, like this number of concentric circles we need to take like this. So, here the magnetic fields are getting added up. So, inside them they are getting added up, but outside if I consider outside, here inside magnetic field is not only because of the above part of the loop, it is also because of the below part of the loop. Therefore, this and this is going to add up, and because of this part also it is going to add up, but outside it is only because of the upper part of the loop, and here also it is only because of the lower part of the loop. Therefore, this magnetic field is very much less compared to the magnetic field inside. Why? Because here magnetic field is because of this part, this part, this part, this part, this part, like this infinitesimally small elements we divided. So, there will be a number of current elements which are responsible for the magnetic field inside the solenoid, but outside it is only because of this part, because of this part, only because of the outer part. So, it here only magnetic field, this magnetic field is responsible only because of the outer part of the solenoid, but here the magnetic field is because of the entire part of the solenoid. Therefore, here B is very large. Suppose if I divide this into 1000 small parts, then magnetic field inside will be because of 1000 times of the each one, whereas outside it is because of only one. That means here if it is B, here if it is, then here it will be 1000 times B. 1B is negligible compared with 1000B. Is it clear? So, what I am doing means I am repeating it once again. If you take this is the turn, circular turn, and current is passing in this way, then magnetic field lines will be like this. Magnetic field lines will be like this, encircling the conductor. So, here if you consider, the magnetic field will be directed in this way. Outside it is directed like this. So, here if you see, this magnetic field is directed upward, and here the magnetic field is directed downward. So, this will be cancelling each other. If I take side by side loops or side by side turns, because of this one it is like this, and because of this one it is like this. So here it is going up, here it is coming out. These two will cancel. So in this direction, one is going up, other is coming down. So they will cancel each other. Therefore, in this direction, perpendicular to axis of solenoid, there is no magnetic field. Above there is a magnetic field, that is only because of this upper part. But inside there is a magnetic field because of the entire loop. Therefore, if this turn is divided into, each turn is divided into 1000 times, 1000 small elements, then the magnetic field is inside because of the 1000 small elements. Therefore, I can take it as 1000B. But outside it is only because of the single one, that is B. So 1000B is very large compared with this B. Therefore, B outside the solenoid will be negligible, whereas B inside the solenoid will be very large compared with the outside one. That's why, and here, well inside the solenoid, all the directions are tangentially directed in the same way. Therefore, we need to add them. Is it clear? That's why this is current I entering and here current I is leaving. Therefore, here magnetic field will be almost negligible, not zero. So here magnetic field will be very large because we are adding up all of them. Here magnetic field will be negligible. Why? Because of these elements there is a magnetic field, but that is very, very small. This is very, very small, but inside it is very, very large. Is it clear? So magnetic field lines will be indicated in this way. So this is the representation of magnetic field. So at the edges of solenoid, does the magnetic field is uniform, is the question. At the edges of the solenoid, the field is not uniform, but it is uniform well inside the solenoid only. Be cautious. If you consider solenoid, magnetic field is uniform well inside the solenoid, but not at the edges. Just like in the case of capacitor. If I take a capacitor, generally speaking, we will say that the field inside the capacitor is uniform, and we will represent the field like this, starting from positive terminal and then terminating at negative plate. Like this, the field is uniform. So capacitor is a device which is used to produce uniform electric field inside the capacitor, but at the edges it is not uniform, it is non-uniform. Capacitor will also producing non-uniform field, that is only at the edges, and that is called birefringence effect. In the similar way, here also solenoid is used to produce a uniform magnetic field only well inside the solenoid, but at the edges the field is non-uniform. Is it clear? And what is the infinite length solenoid? A solenoid whose length is very large compared with its radius of cross section is said to be the infinite long solenoid. Understood why the magnetic field above the solenoid or outside the solenoid is almost negligible and inside the solenoid it is uniform, means the reason is this. So outside magnetic field is responsible only because of the outer part of the loops, but inside magnetic field is because of the every part of each turn, because of this turn, because of this turn, because of this turn. Each turn can be divided into a number of elements. Therefore, all those magnetic fields will add up, and the directions will be like this. They will be tangential. And perpendicular directions, if you consider, because of this and because of this, if it is like this and this will be like this, so because of this upward and because of this is downward. So these two are cancelling each other. Therefore, magnetic field perpendicular to the length of solenoid will be 0. Is it clear? This is about the solenoid. So whenever we require the uniform field, we are going to use the solenoid. Next is about the toroid. Optical purpose, we require high magnetic fields. What is a magnetic field that is produced by the earth? The magnetic field produced by the earth is of the order of 10 to the power of minus 5 Tesla. Tesla is the unit of magnetic field, and practically if you consider the magnetic field of earth, it is of the order of 10 power minus 5 Tesla. Tesla is the SI unit of magnetic field, and the CGS unit of magnetic field is Gauss, G-A-U-S-S, Gauss. 1 Gauss is equal to 10 to the power of minus 4 Tesla, or 1 Tesla is equal to 10 to the power of 4 Gauss. 10 to the power of 4 Gauss. Gauss is the name of the scientist. In order to respect him, we are taking his name as the unit for magnetic field, and it is the CGS unit. So Tesla is a practically larger units, and here the magnetic field produced by the earth is of the order of 10 power minus 5 Tesla. Therefore, if you want higher and higher magnetic fields, why we require higher and higher magnetic fields. So nowadays we are having the nuclear power plants we are having, which are used to produce the useful electricity. In nuclear fission reactor, we will be using the nuclear fuel which is kept inside a container in the fission reactor. So there is no problem to confine the nuclear fuel, or in order to hold the nuclear fuel we can take some containers like aluminum cylinders. But if I want to carry out a nuclear fusion reaction if I want to perform, then what is required? Two hydrogen atoms, if they are moving with high kinetic energies, are made to bombard with each other, then nuclear fusion is going to take place. Yes or no? How nuclear fusion is going to take place? When two or more lighter nuclei combine to form a heavier nuclei, like 1H1 plus 1H1 giving rise to 1H2. In the similar way, if you carry on the equations, finally we will be remained with 4 1H1 is going to give 2He4 plus energy. 4 1H1 gives rise to 2He4. Direct last equation I am writing. So intermediate equations I am skipping off here. 24 MeV of energy is released. This is the nuclear fusion reaction. But here, for the nuclear fusion to carry out, what should happen? We require very high temperature. The requirement of the nuclear fusion is, the nuclear fusion does not take place at ordinary temperature. It will take place only at a temperature of around 10 power 6 Kelvin and above. And this 10 power 6 Kelvin can be noticed on the sun's atmosphere. So when you want this much high temperature to carry out the nuclear fusion, we need to generate this much high temperature either by exploding a nuclear atomic bomb. What happens? High energies will be released. So nuclear fusion if you want to carry out, then this much high temperature is required. That is first requirement. Second requirement is, when the temperature is this much high, is there any metal which can hold a fuel? That is the question. Suppose fuel is there, hydrogen is there with me, and this hydrogen will undergo fusion provided the temperature is 10 power 6 Kelvin. So nuclear fusion is going to take place at a temperature of 10 power 6 Kelvin and above, which is available on the sun's atmosphere. But if you want to produce a nuclear fusion on the surface of the earth, then there is a requirement of this much temperature, first case. Second thing is there any material which can hold the nuclear fuel at this temperature? Practically there is no material which can be there in the solid form at a temperature of 10 power 6 Kelvin and above. Then what is, now I want to carry out the nuclear fusion, then what to do? Then the only thing is, we are having the magnetic field. The high magnetic fields are having the ability to confine the nuclear fuel at this temperature. So for that there are devices called, which are used to produce the high magnetic field, which are named as Tokamaks. The Tokamaks are designed in India by IPR instead of Plasma Research, which was situated in Ahmedabad, that is in Gujarat. So this IPR fellows are designing the Tokamaks. Tokamaks are the devices which are used to produce high magnetic fields, which will be used for the confinement of the nuclear fusion fuel, as well as they will be used in the ISROs for specific purposes. So now the India's first Tokamak, if you consider, the name of India's first Tokamak is Aditya Tokamak. Aditya is the name of the Tokamak which was designed in India by the IPR fellows. Now these Tokamaks are consisting of the toroids. Then what is a toroid? It's very simple. Toroid is obtained by taking a solenoid and bending it in the form of a circle. A solenoid bent in the form of a circle is nothing but a toroid. Then I will show it here how we are going to get a toroid. So toroid is a device which is used to produce the high magnetic fields, and here this is obtained like this. If this is a solenoid carrying a current of 5 amperes, hold the two extreme ends of the solenoid and turn it in the form of a circle. Then we will be getting a shape like this. This is nothing but the toroid. And along this axis of toroid, the magnetic field will be uniform at each and every point in terms of the magnitude, but not in terms of direction. So B here, B here, B here, B here will be equal in strength, but direction will be changing. Therefore, magnetic field is not uniform, but the strength of magnetic field will be uniform in the case of a toroid. Now, we are going to calculate the magnetic field well inside the toroid, along the axis of toroid and outside the toroid. So, what is a toroid? A toroid is a device which is used to produce high magnetic field, and it is obtained by bending the solenoid in the form of a circle. And we are going to calculate the magnetic field well inside the toroid, along the axis of toroid and outside this toroid by using the Ampere circuital law that I will show you here schematically. The diagram for toroid will be indicated like this. Now, this is called the inner radius of toroid, and this is said to be the outer radius of toroid. Now, I will show that schematic representation here. Let me choose, this is the circle formed by the inside part of toroid, and this is the circle formed by outside part of toroid. These two are concentric, and here this represents the axis of toroid. This represents the axis of toroid, which are three concentric circles here. Let me choose the inner radius of toroid as R1 and outer radius of toroid as R2, and this you take it as some capital R, where capital R is taken as a mean radius of toroid, which is taken as capital R is equal to mean radius of toroid means inner radius plus outer radius by 2. It is the mean radius of toroid, I can say. Now, these three circles are dividing the entire region into three parts. This is region 1, this is region 2, and this is region 3. Region 1 is nothing but the region within the inner circle of toroid, and region 2 is inside the toroid, whereas region 3 is outside the toroid. First, we will calculate the magnetic field inside in region 1, and then in region 2, and then in region 3 by using the Ampere's circuital law. Before that, here if you see the toroid, here the current is coming out of the plane of board, and it is going here inside. So, coming out, going in, coming out, going in. So, from outside it is coming out, and inner side it is going into. So, coming out, going into. So, I am representing that with the help of encircle dots and encircle intos. Now, here dot indicates the current is coming out. Current is coming out, whereas into will indicate what? The current is going into. So, I am indicating with dots here, says that the current wire is coming out here, and here it is going into. Into is indicated like this. This is into. Into says that the current is going into the board. So, here the physical quantity which is used to represent, which is represented with dots and intos is nothing but the current. Let me take it as I. Here I current is coming out, here I current is entering. Now, what I want to calculate here? First, I want to calculate the magnetic field in region 1, case 1. Case 1, calculation of magnetic field, in region 1 of toroid. Now, for that what I need to do? I need to choose a point in region 1. Choose this point in region 1 and construct an Amperian loop. While you are choosing the particular point, you have to construct the Amperian loop using this point. The Amperian loop must and should pass through that point where you are calculating the magnetic field. Just like when you are using the Gauss theorem to calculate the electric intensity at a particular point, that Gaussian surface must and should pass through that point where you are calculating electric intensity. In the similar way, when you are going to calculate the magnetic field at a particular point, then you need to construct the Amperian loop which is passing through that point. So, this is the point I want to calculate the magnetic field. Therefore, construct an Amperian loop like this. Let the radius of this Amperian loop is equal to small r. Small r is the radius of that Amperian loop. Now, what we have chosen? Choose a point choose a point in region 1 and construct circular Amperian loop. Amperian loop passing through that point. Passing through that point as shown. Through that point as shown. Now, from Ampere's circuital law, what we know? From Ampere's circuital law, closed line integral of magnetic field is equal to mu naught times the current inside Amperian loop. So here, what is the current inside Amperian loop? Here I inside is nothing but current inside Amperian loop. Inside this loop, is there any current? There is no current entering or leaving this loop. Therefore, current inside this Amperian loop will be 0. Therefore, this is 0. This implies, or therefore, closed line integral of magnetic field is equal to mu naught into 0. Something into 0 is nothing but what? 0. Therefore, closed integral of b bar dot dl bar is equal to 0 we had. Yes or no? Now, here if I see, this length of Amperian loop won't be 0. Therefore, what must be 0? Magnetic field must be 0. As this length of the Amperian loop won't be 0, B must be 0 in order to make this product 0. Therefore, this implies B is equal to 0. So, now what we understood, the magnetic field inside the region 1 will be 0 for the toroid. Next, case 2. Case 2, calculation of magnetic field. Calculation of magnetic field along the axis of toroid. Along the axis of toroid. Axis of toroid. Now, what we need to do? Same. Choose a point on the axis of, choose a point on the axis of toroid, on the axis of toroid, and construct Amperian loop, and construct Amperian loop. Amperian loop. So, here Amperian loop is nothing but what? The dotted circle. So, if I choose a point along the axis of the toroid, if this is the axis of toroid, then this is a point on the axis of toroid. Now, construct an Amperian loop which is nothing but this dotted lines. What is the radius of that Amperian loop? Capital R. Now, according to Ampere's circuital law, what I can say? According to Ampere's circuital law, what I can say? Ampere's circuital law, I can say that closed integral of line integral of magnetic field is equal to mu naught into current inside the Amperian loop. So, I can calculate the magnetic field on the axis of toroid provided if I know the current inside the Amperian loop. What is the current inside Amperian loop here is the question. This is the Amperian loop. This dotted circle is the Amperian loop. Inside this, how much current is there? If you see here, here current is coming out of the board and here it is entering into the board. 1 into says that I current is going into, 2 into means 2I current is going into, 3 into means 3I current. Suppose here 3 turns are there, current is 1 turn, second turn, third turn, fourth turn, like this. So, like this turns are there, here the turn is coming out and here it is going into. So, if 3 intos are there means 3 times current is going into. So, 3I current is there inside Amperian loop. So, I have to check out how many intos are there inside this circle. Then, if there are n number of intos, then there are n turns are there. Number of turns into current through each turn will give the total current inside this Amperian loop. So, what is the total current inside this Amperian loop is nothing but number of turns inside this Amperian loop into current through each turn. Then how to calculate the number of turns? So, we know that small n is the number of turns per unit length. Small n is the number of turns per unit length. Then how many number of turns are over this length of Amperian loop. What is the length of this Amperian loop here? Length of this Amperian loop is nothing but circumference of this Amperian loop. Circumference of this Amperian loop is how much? 2 pi into capital R. 2 pi into capital R. Now, I inside is nothing but what? Now, here if I see I inside means here I inside is equal to, let me choose capital N is the number of turns into current inside, current through each turn, where capital N is number of turns. Capital N is equal to number of turns. Then how to find the number of turns? If small n is the number of turns per unit length, then number of turns is equal to, but number of turns is equal to number of turns per unit length into the length of Amperian loop, that is 2 pi into capital R. Is it clear? Where small n stands for what? Where small n is equal to number of turns per unit length. Number of turns per unit length. So, using these two, therefore, current inside is equal to small n into 2 pi capital R into I. Is it clear? Now, using equation 1, what I can say? Using equation 1, what I can say? Using equation 1, closed integral of B dot dl bar, B bar dot dl bar is equal to mu naught into I inside. I inside means what we are having here, small n into 2 pi capital R into I. Shall I take like this? Now, what is that value? I will rub it here. That is nothing but closed integral of B into dl into cos 0 degrees. Why? Because here the magnetic field is tangential to this loop and length element is also tangential. Therefore, angle between B bar and dl bar is equal to 0. Therefore, I can write it like this, mu naught into n into 2 pi r into I. Okay. From this, along this axis at every point the magnitude of magnetic field is same, because it is nothing but when you extend it like this, we will get a solenoid where the strength is same. So, therefore, B is constant, write it outside, into closed integral of dl cos 0 is 1 is equal to mu naught into n into 2 pi r into I. This implies B into what is this closed line integral of this Amperian loop? Nothing but 2 pi capital R. 2 pi capital R is equal to mu naught into n into 2 pi r into I. So, what we are getting from this? This is nothing but 2 pi r will cancel and B is equal to mu naught into n into I. 2 pi r will get cancelled. That means the equation of magnetic field due to a toroid on its axis is equal to the formula of magnetic field due to a solenoid. Or else more clearly, I can also write it like this. This implies B is equal to mu naught into, what is this small n here? Small n is equal to capital N divided by 2 pi r. Capital N divided by 2 pi r into I. This implies B is equal to mu naught Ni divided by 2 pi capital R, where capital R is the mean radius, where capital R is equal to inner radius plus outer radius by 2, where capital R is nothing but inner radius of toroid plus outer radius of toroid by 2. So, this is the formula for magnetic field due to a toroid. The magnetic field due to a toroid is nothing but mu naught into Ni divided by 2 pi r, where r is the mean radius of toroid, n is the number of turns of the toroid, I is the current of the toroid, and this formula is analogous to what? Magnetic field inside the solenoid. So, these two equations says that by bending the solenoid only we are getting the toroid. Is it clear? But the solenoid, when it is bent in the form of a circle, we are going to get the toroid. So, this is how we are going to calculate the magnetic field along the axis of toroid, whose value is equal to mu naught n into I, where n is the number of turns per unit length. Here capital N is the number of turns and length is nothing but length of this Amperian loop, which is equal to 2 pi r. Therefore, mu naught Ni divided by 2 pi r is the important formula that is to be remembered for the toroid case. Instead of remembering this formula, better you remember this formula. If you have forgotten this, remember the formula for solenoid and replace small n with capital N by 2 pi r. Small n is nothing but number of turns per unit length. Number of turns is taken as capital N and the total length is nothing but length of the toroid, which is equal to 2 pi into capital R. Is it clear? This is a formula for magnetic field due to the toroid along its axial line. Now, what we understood in region 1, that is well inside the toroid, there is no magnetic field. But in region 2, that is along the axis of the toroid, there is a magnetic field which is given by mu naught Ni divided by 2 pi r. The third case is, what is the magnetic field outside the toroid? Outside the toroid means I have to choose a point somewhere else here. This is a point which is outside in region 3. Then construct an Amperian loop. Construct an Amperian loop like this. Construct an Amperian loop passing through this point. If you consider this is the Amperian loop, whose radius is equal to some r dash. Now, what is the magnetic field? So, same story is to be repeated. Case 3, calculation of magnetic field outside the toroid. Calculation of magnetic field outside toroid. Outside toroid. So, for that what we need to choose a point outside the toroid. Outside toroid and construct Amperian loop of radius r dash as shown. Now, the story repeats. According to Ampere's circuital law, we will be knowing this formula. Here, what is mu inside is the question. What is mu naught in, sorry, here what is I inside is the question, not mu inside, I inside. What is the value of current inside this Amperian loop? If you see here I current is coming out, I current is going into. So, 3 ampere coming out and 3 amperes going into. Then what is the total current? 3 coming out if it is taken as positive, going into is taken as negative. Plus 3 plus minus 3 is 0. So, I coming out, I going into. So, cancel. So, this is coming out, this is going into. They are cancelling each other. Therefore, how many number of turns are there? If n number of turns are there means Ni is the outcoming current and Ni is the current going into. So, Ni is the outcoming current and Ni is the inside current. Then what is the total current means? This is plus Ni, this is minus Ni. So, what is the total current inside this Amperian loop? 0. Here I inside is equal to n into I plus minus n into I, where n is the number of turns. Therefore, I inside is equal to 0. Hence, what I can say, closed line integral of magnetic field is equal to mu naught into 0. This implies, just like in first case, B is equal to 0. So, finally what we can conclude means there is no magnetic field well inside the toroid and outside the toroid. There is a magnetic field only along the axis of toroid and whose value is equal to mu naught Ni divided by 2 pi capital R, where n is the number of turns of the toroid, I is the current and R is the mean radius of the toroid. Is it clear? This is about the toroid. So, toroid is a device which is used to produce the high magnetic fields and these will be used in the Tokamaks where the Tokamaks are used to produce the high magnetic field which can hold the plasma state. So, for the confinement of plasma or high temperature fluids, if you want to hold, then we require a container. That container is provided by the magnetic field. There is no physical container here, but there is a hypothetical container called or a theoretical container called magnetic field. The magnetic field is having the ability to hold the nuclear fuel in the air medium. Is it clear? That is how the toroids will be useful. Is it clear?